Hello, folks. Let's wait for 2 more minutes and then we should get started. Okay. Hope my screen's coming through.
Looks good.
Good day, everyone. Welcome to the 15th annual workshop on the energy efficient HPC working group. Today is day one. This will be a 2-day virtual workshop. Same start time as today, but tomorrow as well. On behalf of Torsten and the rest of the HPC working group, workshop committee, I'd like to welcome you all. I'm Sid. A few logistics very quickly. The workshop event website is listed here on the screen. It should also be part of your meeting invite. The website includes agenda with session abstracts, speaker bios, and at the end of the conference, we'll make sure to upload all the presentation materials there. And the working group website, so the workshop itself is organized by the Energy HPC working group, and the website for which is on here. A few notes on etiquettes. As always, please mute your microphone and turn off your webcam when you're not presenting or speaking. This should help us save on the combined network bandwidth. A few other notes, questions and answers or any other comments, I'd request everyone to please use the Zoom chat box and refrain from using the Q&A button right here. That is something that we are not monitoring. So I request all the individual session leads and the moderators to please keep monitoring the chat box for any questions and comments. A quick look at the agenda. It's a 2-day event, as mentioned earlier. Day number 1, we will be focusing on motivating end users for energy efficiency across the system stack. That will be more of a panel-driven session. We will then have some of the latest updates and insights about the Green 500 measurements methodology. And then following that, there will also be a discussion about sustainability metrics for impact, another panel session there. Tomorrow, we will have 2 invited talks and an audience-driven participation. So please also do join tomorrow if time permits. There will be a discussion. There will be an invited talk on maintaining large-scale sustainable systems, right? Always focusing on energy efficiency is not the goal. There are many other things you need to be mindful of when you're trying to design a sustainable system. And that will be one talk. The second will be really an audience-driven session where we would expect the audience to participate and chime in as much as possible. That will be a focus on advanced facility cooling controls, where we would like to really solicit lessons learned in that field. Another very exciting talk will be on policies and technologies surrounding sustainability and AI. Another invited talk, and we hope to learn more on that front. And then we would, of course, wrap it up with some closing thoughts. With that, a very quick overview here. The first session will be a panel, as mentioned earlier. Matthias Maiterth from Oak Ridge will be driving this session. Matthias is a postdoctoral research associate at ORNL. His research focuses on HPC and AI to improve performance, energy, and power efficiency of large-scale systems. Before joining ORNL, he was an academic research staff at TU Munich, and he acquired his doctoral degree from LMU. And the doctoral study itself included a lot of exchanges as a visiting researcher in collaboration with Lawrence Livermore efforts. So that was a 3-year funded research on that front. So with that, Matthias, over to you. I'd let you introduce your panelists.
Not quite. I have to correct you. The 3-year funded research was at Intel, not at Livermore. But thank you for the introduction.
Gotcha. Right. Thanks.
I'm going to share my screen. I sent a request to share the screen. Yeah.
Natalie, do you have the permissions to do that?
Be able to. Do you see my screen?
No, not yet. Sid, if you can stop sharing, that might work.
I can see your screen.
Okay.
Yes, now we can.
Okay. Okay. So today's first session is going to be on motivating end users for energy efficiency. This is short presentations by the panelists, and then we're going to follow up with discussions. And for that, I have some questions prepared, but feel free to raise questions in the chat or raise your hand and unmute to ask questions. We have 4 speakers. I've got to get my stream out of the way. Okay, good. So we have 4 speakers from a very broad background, which is actually really good to motivate what end users can do and how do end users actually interact with systems. We're going to start with Dr. Fumiyoshi Soshi. Fumiyoshi received his PhD from Kanazawa University in Japan in 2000. In 2006, he joined the Riken-K Computer Development Project as R&D scientist, and later was also involved in the Fugaku Development Project. In his role as team lead, he was awarded the ACM Gordon Bell Prize in 2011. And since 2012, he is Division Director of the Operations and Computer Technology Division at Riken RCCF. And his division's responsibilities are the operation and enhancement of Fugaku and its facilities, including substations, chillers, gas turbines, generation, air handler, among others. So very excited to have him to see the systems perspective and what they did to cope with some of the enabling energy efficiency at the center. And as next speaker, we're going to have Luca Berto. He is a computer scientist and graduate of University of Milan and working at Eni now. His past experiences are a software engineer, including imaging processing, information management, and large-scale network and host monitoring. In 2009, he was part of the team that designed and built Eni's Green Data Center. And 2013, he joined Eni as data center architect. And since 2017, Luca Berto is IT architect project lead for Eni's HPC department. And his job role now is titled HPC knowledge owner. So we're very excited to have him here and present on what Eni is doing with system software to improve energy efficiency there and interaction with the users. Then we're going a bit more towards the application side. And we have Dr. Osman Sekin-Simzek. Osman is a postdoctoral researcher at the HPC group at University of Basel, and he is part of both the PASC SB Extra 2 and the SKACH projects. and he's responsible for load balancing, energy efficiency measurements for the SPH-EXA simulation framework. And before that, he was a postdoctoral researcher at the University of Manchester in the EuroEXA project, porting the LFRIC weather forecast application onto FPGAs. The Simsek received his PhD in 2019 from the University of Manchester, and that is titled Leveraging Data Flow Task Parallelism for Locality Aware Dynamic Scheduling on Heterogeneous Platforms. And his research includes topics in high-performance computing, scheduling, energy efficiency, and heterogeneous programming. And as a last speaker, we have Daniel Arndt from Oak Ridge National Lab. He is working on the COCOS project. Dr. Daniel Arndt is a computational scientist at the Oak Ridge National Laboratory in the Scalable Algorithms and Coupled Physics groups. He is formerly a postdoc at the University of Heidelberg and worked with Professor Kanchat in the Mathematical Methods of Simulations group. And before that, he was a member of the Numerical Methods for Partial Differential Equations group, supervised by Professor Lube in the Institute of Numerical and Applied Mathematics at the University of Göttingen. And his current focus is on backend implementations of COCOS, in particular focused on SQL and focusing on applications for large-scale computational sciences. So really great to have the panelists here. And we're now going to go to, I asked each of the speakers to prepare 3 slides and then tell us a bit about their background so that we can engage in questions with them. With that, I would ask Fumiyoshi to take the first part of the presentation.
Yes, thank you, Matthias. So yes, everyone. So I'm Fumiyoshi. So as Matthias introduced, I'm the division director of the operation division of the RCCS RICAM. So my original background is theoretical physics, and especially the high energy physics and by the computer simulations. So anyway, so my current mission is the operation and the enhancement of the system, and especially for the energy and the energy efficiency and the carbon neutrality and so on. So the primary trigger that we addressed. So please move to the next slide. Okay, so yes, this is so. Yes, the primary trigger that we address the energy efficient operation more aggressively was the energy crisis in 2022. So this graph showed the history of the gas and electricity rates for the 3 years before and after the COVID-19 pandemic. So the rates normalized them in April 2019. So as you can see, during the pandemic, the prices got cheaper due to a lower economic activity worldwide. Then the prices were getting higher so rapidly due to the resumption of the economy and the Ukraine crisis and the exchange rates between US dollar, euro, and Japanese yen. So Japanese yen was relatively so weak. At peak, the prices doubled compared with those before the pandemic. So since it was clear that our annual budget would be exceeded, so we decided to shut down 1/3 of the Fuga system for 3 months to reduce the power consumption. So next slide, please. So we also addressed the more aggressive use of the power saving function in Fugaku. So the function consists of the core retention and the eco mode. So the core retention can save standby power for either core, and the eco mode corresponds to the disabling one of the 2 FPUs. So user can control these functions via Power API. And so first we informed the user that our budget would be short due to the rapid increase in energy cost. Then we requested that the user use the function to reduce power consumption. So many users understood the situation and cooperated with power saving operation using the functions. So we could avoid the crisis in 2022. So next slide, please. So in next year, 2023, so energy prices were still high. So we had to continue power saving operation. So we introduced an incentive program for cooperation in the power saving operations. So it's the Fugaku Point program. The Fugaku points quantify cooperation in power saving operations. Depending on the points, the user can execute their jobs with higher priority during the specific periods. So next slide, please. So these slides show the results of the program for the 2023. So, I'm sorry. So yes, it's okay. So the table compare, so upper table, they compare the first and the second half of the 2023. You can see number of the projects that earned the points and the average point are increased. So this means that this program would be recognized by users, and the number of users aware of power saving operation will increase. So the average power consumption per node is also improved. So we are now trying to clarify that the power savings contributed to energy savings by comparing energy consumption before and after applying power saving functions for the same job. So this is the primary result. So this work has been essentially done by the Dr. Kodama. So this preliminary result shows that power saving contributed to energy saving. So the energy consumption could be reduced by the 11% on average by applying the power saving functions. So our next step is to improve the definition of the Fugaku point. So the current version of the points does not consider the power consumption profile for each jobs and the code tuning efforts. So this is not fair. So we try to define the new Fugaku point, including such a point. Okay, thank you very much.
Thank you very much for that introduction. And I clicked on the slides too much in the beginning, so sorry for that. Next, we have Luca Baton to speak about their efforts on the system software side.
Hello, everyone. And I will start stating that my presentation is obviously off topic because I'm not talking about energy saving. I'm talking about increasing cluster usage. And I'm not talking about how to invite users to change their attitude towards the cluster usage, but we have done something without user intervention. But if you have complaints, please refer to Matthias because he was informed of that before I submitted my presentation. Next slide, please. The starting point was some 8 years ago when we looked into our cluster and we noticed that we had several nodes entirely unused. And looking into every single node, both the CPU and the GPU were hardly used to an acceptable level. So being a private company and not a research lab, our primary goal is to exploit as much as possible the investment we made with this cluster and obviously to increase the usage in order to achieve more work per time unit. So this was the situation in the beginning. Next slide, please. And we can split the problem into two different problems. One that lies inside the single node, how to better exploit the resources available into the node. The other one, how to use effectively all the nodes available. What I've called intra-node optimization and inter-node optimization. But what we did is basically changing the way we use the job scheduler. And we introduced a scheduling mode that we call the node sharing. There's no rocket science in what we did. These are all technologies already available since many years. It's just a particular configuration that we used. Node sharing means that we let more jobs run on every node. The reason being that any code can hardly use at once all the resources available to the node. Especially if you have MPI jobs, they have sometimes data exchange moments that let the compute units idle if you don't have proper overlapping. But even if you do, you will never see, except for maybe the benchmark, a code that is able to exploit all the CPUs, all the GPUs, the network, the disk, all together all the time. But what happens if you have more jobs running on a node? When job one is idle on the CPU because it's waiting data from the disk, for example, job two may exploit the CPU let idle by job one. And this is the basic principle. If we have more jobs, we have more chances to use the compute resources available. There's a limit into this approach. And the limit is that every job has to be able to declare how much memory it will use, because you cannot allow the jobs to allocate more memory that is available on the node. And this somehow limits the range of application of node sharing, because only codes that are able to preview the memory usage can do that. Except for that, the compute units are overbooked. And as I said before, this allows to use them at a higher level. Talking about the idle nodes, we had a very naive approach in assigning the nodes to the different projects. We have weekly meetings where every project leader was exposing his needs and was granted a certain number of nodes for the forthcoming week. So this was a very static subdivision of the cluster. And the problem is that you're not guaranteed to use the node you have been granted for the whole time. Maybe you need some time to prepare the data. Maybe you finish a day before the end of the week, or the rest of the time your node gets wasted. So what we did is to change the approach. Instead of, because we still need to assign resources proportionally to the value of the projects, in our case to the business value, we assign a priority and let the scheduler run the jobs in priority order, which means that if everyone is submitting at full rate, the cluster will be split into parts that are proportional to the priorities. But if someone, for any reason, is not using his nodes get assigned to other jobs. That way, to other jobs. That way, we achieve a higher node usage, which is basically 100%. Next slide, please. And this is the result. these data are a little old. Node sharing gave us a nice boost in terms of throughput, from 30 to 40%. Of course, this depends on the kind of jobs you're running, because the more diverse the resource usage is, the better. And the best match is to have one job that is CPU only with one job that is GPU only, for example, because they can share the node perfectly without slowing down, just like if they were given a dedicated node. In real life, the results are vary with the kind of code. And in the lower chart, you see the result of the fair share. As you can see, this is a stacked chart where the summary of the nodes, of the used nodes, is almost always 100%. And there you can see how the system assigns and removes nodes depending on the state of the different activities running into the cluster. And we increase the usage from 80% to more than 90%. And that's it.
Thank you very much. Very interesting. We're gonna continue with the short presentation by Osman.
Thank you. So for the past 2 years, I've been working on the SPH EXA astrophysics framework, which is a particle-based framework for running large-scale simulations. It's highly scalable and high performance. So we are generally using a lot of nodes and GPUs to run our application. So we started thinking, oh, we should look into maybe also optimizing for energy efficiency rather than only focusing on the performance aspect, which is why we have been doing some experiments and trying to tweak with the GPU frequency of our code, which runs natively on GPUs. We don't use CPUs mostly, so my talk is going to be focusing on a little bit from the user side perspective, maybe a little bit for example, how users can look at their code and try to improve energy efficiency. Yeah, so what we started with is to instrument SPH EXA to include basically energy measurement as well as timing data, because we were normally timing each of these functions that you can see on the screen to see how long each function was taking. So we did a little bit more instrumentation, and now from all ranks we get timing data as well as energy data. How we did this was we generally target gray built systems, and they provide something called PM counters, which can be read directly from the system. You can read the CPU, GPU, and memory and other auxiliary parts for each blade, the energy consumption. And this is basically what we are doing. And we tried on different types of simulations as well as different systems. And what we see is kind of what we expected is that it depends, the energy consumption depends on the type of simulation. So different simulations parts will have different energy consumptions. For example, on the right-hand side, we simulate an average collapse test case, which includes gravity. And on the left-hand side, we have a subsonic turbulence test case, which doesn't include gravity. And we can see that the effect of gravity for energy consumption overtakes what was previously the most energy consuming part of the simulation code. The energy consumption obviously depends on whether the part of the function is compute intensive or memory intensive or IO. But we don't need to specifically go into every function to find out how much compute intensity there is versus IO or memory. We can just get this data and look at the code from a little bit coarser perspective, which can be orthogonal to other energy efficiency methods that can improve the efficiency. Next one, please. Yes, so generally what we tried was to change the compute frequency of the GPU to a static value at the beginning. And what we see on the left side is that as we decrease the frequency, we get like 20% less energy usage, but around 18% more in time to solution. So these metrics combined is called energy delay.
The audio for me is broken.
Much.
Okay.
But what we see. Hello?
You're back. You're good.
Okay. On the right side, what we see is that the different functions obviously gets affected of differently by the changing frequencies. So what we try to do next is that if we can go to the next slide.
Mm-hmm. Oh, yep.
So what we try to do is to set the GPU frequency from within the code using the NVML specific functions, and where we can get the best energy consumption, but not losing much of the performance. For example, we limited the performance loss, like time to solution increment to different levels up to 5%. And then we selected basically the best performing one, and then tried those frequencies running multiple simulations to see if they hold. And what we got at the end is that if we can move forward, yeah, what we get is 3% slowdown and 8% energy reduction. And this shows that EDP is like lower than the static ones, static frequency changes, and it is more stable. One of the reasons why this method worked better than depending on the DVFS is that GPU's DVFS is generally not as good as CPU. So for example, it just looks at whether you're running something or not, and the utilization data it depends on is not very accurate. So statically, well, not statically, dynamically changing during the execution to the frequency levels, which we found to be more energy efficient, gave us better gains. So these experiments are unfortunately done using pseudo, because for changing the GPU frequencies, that's what I used. But now that I learned that with support from admins, we can allow admins can allow users to change the GPU frequencies from the user level, but I haven't tried that yet. But what I wanted to show is basically there are ways that we can, from the user side, increase the energy efficiency of our codes, but may need some support from the system admins to do so. Thank you.
Yeah, thank you very much. And to transition to the next talk, that's exactly why I coupled the speakers like they are. Here you see that it's actually quite an approach to get codes energy efficient and a lot of probing, but how can we actually do this from a programming language framework? How can tools support us on that? And For that, I would ask Daniel to present.
Yeah, thank you, Matthias. I'll represent Kokos today and see what we can do with respect to energy efficiency. Next slide, please. Kokos is a C++ programming model for performance portability, if you're not aware. So we are trying to target the big machines, and it gained traction in particular with the exascale computing project, which just ended, where Kokos is probably the most successful performance portability framework, where like around 50% of all codes that use C++ rely on Kokos. In general, we try to align our development with the C++ standard, and we have multiple components that are important for users. On top of the base Kokos, there are math libraries that represent like BLAS functionalities or linear algebra. But then also more important for this audience is that we have tools for debugging, profiling, and tuning, that are always on, so that you can, without changing your code, look into monitor your code and apply various hooks. We also have interoperability with Fortran and Python, which is important for a wide audience of project in ECP. And all our project is open source, and you can look at it. Next slide, please. So the particular pillar that is important here is Kokos tools, which means that on every call to say like a parallel construct, we invoke hooks that inform tools about the parallel dispatch that happen, about allocations, deallocations, deep copies. We have region markers, which is explicit markers that the user needs to employ. And we have a bunch of information in there, like where it run, what was the kernel name, and of course what the event was. And the important thing, it's always enabled. So using all of these doesn't actually require users to change their Kokos program. So the usage is via shared libraries. So we just like DL open particular tools. So you would normally just export the respective library name as an environment variable, and then just run your example, your application, which makes it very easy to use. Next slide, please. So how this looks like is basically that we have a C-type interface, and as an example, I have here a parallel for hook. So we see that we get the name of the kernel, we get the device ID from which we know like on which kind of GPU or CPU it was running, what kind of execution space instance, like was it what kind of stream it was, and in general, just what kind of resource it was, like a CPU or GPU. And we can then also do something with the kernel ID. So these hooks are used in various ways. We have some predefined tools which just tell you about the execution, or like the profiling in terms of like runtime with space-time stack, which kernels took the longest, what were the maximum allocations, or just like a time series of events that happen, which helps with debugging. You can write your own tools with this. And what's interesting here is a little bit the connectors to third-party tools. We have like VTune, Timery, Caliper, but most importantly, a Variorum connector, which allows to monitor power consumption any point in time, and possibly like then also a frequency. And this is something that we want to expand upon. In particular, and going forward, we could envision to also deploy a power cap tool, so that you can not just monitor what kind of power consumption you have per kernel, but then also give the application like a profile or tell the respective resource when to cap power to optimize performance. We also have a tuning interface, which we could couple with that. From a facility point of view, it's also interesting that facilities can just enable some tools and enforce them by setting these environment variables, in particular since they are chainable. And this way, it's much easier to get the users to actually care about power, or make it easier for them than to optimize for power consumption. And that's it from my side.
Okay. We have one question directly to our talk, and I'm also going to have one question for Yoshi. So the question in the talk, in the chat box is, what kind of system are you using? Short outline, and how did you implement the overbooking?
We currently have 2 clusters, both around 2,000 nodes each, with NVIDIA GPUs, V100, 2 flavors, because NVIDIA made the V100 for oil and gas later, when we made an upgrade of the of one of 2 clusters. Roughly 200 gigs of memory each, and this shared storage cluster of roughly 40 petabytes. I have to say that these systems are more than 4 years old now, and we are now in the path of releasing the upgrade, which will be our next due for end of 2024, which will be AMD 250X based, well, the same architecture of Lumi and Frontier, with 3,500 nodes, if I remember correctly. That will be our next one.
Okay.
And about the overbooking, no, we don't use virtualization. We simply let more process run on the same operating system and let the kernel do its job. That is time sharing the processes, both on the CPU and the GPU.
And then I would go to a question from Yoshi. I think this strategy with the Fugaku points is very interesting. Can you elaborate a bit on that? How you came up with that and how easy it was to basically put into basically an operational mode?
So yeah. So the current version of the point is the just subtraction of the energy. Okay, so this is very simple. So subtraction of the standard energy consumption and the minus and the real energy consumption. So if every job execute with the standard energy, so our annual budget and the energy expense are consistent. Okay, so in that sense, so as I mentioned, so this definition does not consider into the power job profile variations and the code tuning efforts, something like that. So we have to take into account such a point into the next version of the point.
Okay. With that, I'm going to stop sharing and basically go to general questions for our 4 panelists. I have a few prepared. I see that already some of them are coming into the chat box, but I would like to start with Osman and ask him, how easy is it for users to actually, I really compiled this group of speakers so that we have from the systems and going closer and closer to the applications. So how easy is it for users to make such considerations or even switch an algorithm to go from one that is high performant to one that is energy efficient? So is that possible, or how should energy efficiency HPC working group is basically not so much from the application side, but has a big focus on the system side. So if you speak to that, I think that would be very helpful for us.
Yeah, thank you for the question. So as we all know, performance also has an effect on better energy efficiency, since the energy is over time, right? So if we decrease the amount of time spent for our applications, we are more energy efficient. So it doesn't necessarily mean that we are, at least in our case, let me say, because there's another aspect to this, it doesn't necessarily mean that we need to switch over from performance tuning to energy tuning. It is just on top of that. So there are a lot of studies that show basically as we increase parallelism or increase the resource usage, after some point, the energy consumption comes to a valley and then starts increasing again. So I think we need to improve the performance of our applications first to find the least amount of time to solution, and then see if we can decrease the energy a little bit further without losing performance. That is actually what we are trying to achieve here, to find the sweet spots for the applications.
But that's very hands-on, I assume, and really digging into the code and making the changes.
Yeah, exactly. So there are a lot of things, great things that have been already proposed from systems side, from like runtime perspectives and everything. But what we found is that the user level was not studied a lot. So we thought, okay, we have this code. We are quite hands-on with our code anyway. So let's see if we can improve the energy usage a little bit more. For example, we have a very extreme scale allocation on Lumi supercomputer right now, and it's been going like half a year now. If we could apply some of the things that we found out to that, we can definitely decrease our energy usage to maybe like tens or hundreds of megawatt hours when we are running the largest scale simulations. Mm-hmm. So I think all the things that are being done from system level, runtime level, job level are extremely good, and user level kind of tuning can be orthogonal to each of those to have a great energy efficiency for all the codes that we can run.
But Luca, you explicitly mentioned that you didn't want to basically be invasive and change what the user does, but support him through basically what the system can do underneath. So why that choice? How easy would it be to actually change the tools, the setup that the users are using, or does that have to be completely transparent? How is that at the organization?
Yes, it's important to note that what we can do probably cannot be done in every lab, because we are not a research lab, we are an industry. And that means that we have few controlled codes running. We don't have the plethora of different projects running on an institution, and our users are very educated and can usually they are not they don't have a computer science background. They are focused on their job, and the HPC is a tool to them. So that said, we cannot expect them to make meaningful choices and decisions regarding the the optimal usage of the system. They just have a user interface. They request some kind of computation, and the system in the background makes the decisions that best fit the request. For example, our users don't even know that job exists. They only know that they need to perform a certain kind of computation, and then they launch it, and after some time they have a result they can work with. Behind that, there is a workflow manager that spawns jobs, collects partial results, do checkpointing, and everything that is done in an HPC system. But all of that is hidden to the users. So regarding the scheduling mode that we have, the applications are able to declare the resource they need so that they can run in node sharing. They get submitted the jobs by the workflow manager, and the fair share chooses, depending on the state of the cluster. The cluster, the scheduler has two informations. He has a target, which says every project how much resources deserves. And on the other side, he sees every project that is actually running, how much resources is using. And comparing those two states, he can decide which job is the next one worthy to be submitted, to be executed. All of this happens without user intervention, and the system automatically adapts in order to satisfy the request, respecting the priorities decided by the business. And we are also able to change dynamically those priorities without the users even knowing that their project has been raised or lowered in terms of priority. All of this to say that the users are unaware. Our goal is to maximize the use of the cluster, and this could translate in more efficiency, for the simple fact that if I can do the same job faster, I could buy a smaller cluster instead. So reducing the overall power envelope. But this is not to replace what I've seen exposed by other speakers, because it is certainly possible to mix what we have done, for example, with the optimal frequency on the GPU. I know Cocos, who doesn't know, is very well established. We are basically software engineers, and so we are used to write our software down to the smallest optimization. So maybe this is not our bread and butter, but for other kind of users, this is an approach that could mix with our node sharing or whatever. Node sharing can be used everywhere.
I'm gonna summarize two questions. So with what you just said, one question was on how do you actually account the information as in resource usage and, for example, also energy accounting if you do so, and how do you measure performance implication? That is basically handled by workflow engine, scheduler, operating system, and the goal is effective resource utilization. And you care about that where the user is shielded from that. Is this correct if I summarize it like that?
Exactly.
Okay.
And I want to answer Thomas, who asked about the problem of accounting. Actually, this is a problem with node sharing because you cannot tell how much resources every job is using in a single node. This is a problem we don't have because we don't care. We don't have to make our groups pay for the resources. The HPC is a company resource that is used by everyone, again, depending on the business value. But there is no need to account the whole time per project. This could be an issue. On the CPU side, you may think of wrapping every job with a time that tells you at the end how many CPU clocks have been used. Maybe it's harder with the GPU, but don't know if you have the counters. Probably yes, but again, this is something that we don't do, and I think that could be an issue.
Mm-hmm. I'm gonna move the discussion towards Daniel and ask the Cocos performance interface, or the profiling interface, sorry, that is really intended for tools to interact with the environment. How easy is it to shift this from tools, as in performance debuggers and so on, to a always on? The system uses these to manage the environment. Are they mutually inclusive? And yeah, that would be interesting how to shift that.
Yeah, you're right. At the moment, it's mostly the users provide wanting to use some tools to profile their codes. But ultimately, it doesn't really matter where the tool come from. It's just the question what kind of tools were developed. So we have the hooks that can give you information about like when, I mean, that get called whenever we run into like a region or parallel 4, and we know about the name and the device. And this is not a problem for, like, say, facilities to hook in to get more insight about the program that is running in terms of power, frequency, or whatever is interesting. And we also have the capability of nesting these tools. So you can just say, first, I call whatever the facility wants, and then on top of that, I use whatever the user wants. So that's pretty easy. I think like what we are missing is really then the interaction more with the facility, interested in writing these tools, interacting and saying, like, whenever we launch a job, we define this environment variable or enable our own tool. So we have to have discussions on what's interesting and what the interface should look like there.
Mm-hmm. And for my basically last question that I've prepared, I'm going to go again to Fumiyoshi, and I had one with incentives, I think with Fugaku points that is really well explained. The others were on how easy was it for users to actually accept that, and one that is actually that I want you to address first is, so with the knowledge that you gained over these projects and actually the kind of situation that you had to react to, if you knew what you know now, what would you do differently if you had to go into the same situation again? So yeah.
Yes, so as I mentioned, so the situation in the 2022 is very urgent. So we had to take act something quickly. So we introduced the simple version of the points, and so we informed this situation to the user, and so fortunately they have the sympathy to overcome the crisis. So it worked very well, I think. So so in next phase, so we have to we have to design these frame. How can I say? We have to design in the framework to sustainably work. So in that sense, we introduced the we have to improve the next version. We have to introduce the next version of the FLAG point. So which include the power consumption profile variation for the jobs and the cold tuning effort or something like that. So in the we feel this kind of the system works well. In the the other point is this: we have many options to reduce the energy consumption in our system. So actually, we have already power node or to reduce the power consumption of the facility side. So we don't have such a many options. So if we face the if I go back to the same situation, so I think we have no such a many options. I think. Is this the answer for you?
I think that's a good answer, especially so luckily in Fugaki you already have prepared the processor with the echo mode, echo boost mode, and so on. So without that foresight, I assume you would have had a way harder situation to react to this. Yeah, really interesting. We're at the top of the hour, but I was informed that we can overdraw a bit. So Thomas and Sid, please stop me if we're basically if we should transition. But if the speakers have questions for each other, yeah, please feel free to basically point and ask some things where you're curious about how that actually works in the respective organization or with a code to actually get to specific parameters and tuning.
Yes, if possible, I would like to make a question to Fumiyoshi-san. Because was 2 years ago in Bologna, they had a presentation showing their approach to energy saving. And they said that it was preferable to use less cores at higher frequencies, energy-wise, than using many cores at lower frequency. I'm sure that you just made it, and so this is true. But this is surprising for me because, in theory, the increase in frequency should cost in terms of energy at the square. So it would be more natural to think to have many slower CPUs than few very quick CPU. How did you justify this behavior you have in your system?
Oh, thank you for your question. So, first of all, our CPU does not have the many frequency mode, just only 2.0 and 2.2. So that's only 2 options. So they are not not flexible. This is the first point, and the second point is we don't have such a data so far. So we have to analyze. We have to investigate such aspect from now on. I'm sorry.
No. This is something that I've waited to ask you for 2 years because this really shocked me when you saw it. Okay, so thank you for the answer.
So one point I'd like to say there are many jobs that the full core that does not use the full core. So in many jobs, many core does not use. So we are now investigating quantitatively. So just an ongoing project.
Thank you.
Thank you so much.
If anyone of you still has questions, Thomas or Sid didn't say anything yet to stop, please feel free.
Yeah, I have a quick
Osman.
question.
Oh, yeah, okay.
Sorry. Yep.
Yeah, Sid.
Question for Daniel Kokos. With regards to higher level tools using Kokos to monitor the underlying platform, you also mentioned somewhere on the slide there was a reference to also controlling the knob, not just monitoring, but actually like enforcing power cap. Are those a different set of APIs to be able to do that, writing versus reading counters?
I mean, actually, this doesn't exist. I was just pointing out that that could be a possibility for developing a tool that would actually set power limits. I mean, the problem we are facing right now is that the systems we're running on don't allow us to do that anyway. So we need some more of the system, basically special queues or whatnot, where we have the ability to set power caps and see that if this has an impact. But I mean, theoretically, this should not be much different. You would just need to pass in information about what kind of kernels you want to power cap or when. And so whenever you hook into this tool, then it could invoke this capability and say like, okay, at this kernel, I want to run with a lower frequency or something like that.
Gotcha. Okay. And is the execution model of the framework, the monitoring part, is it more catered towards in-band monitoring versus out-of-band across the network or over BMC type monitoring? Would you say the framework is appealing to one type more than the other?
I mean, in general, Quarkus only really cares about node level performance anyway. I mean, Quarkus is a node level type of program model. Like we don't have any MPI, so we really would only care about like particular cores, like particular cores or GPUs.
Understood. Thank you.
And I think the information how you can actually mark up and annotate codes would even allow you to mark up regions where you're in MPI. To, for example, say, oh, I'm now interested in network region. I say, okay, I tag the specific MPI call and then get information using the same interfaces.
Yeah, exactly. So we have the hooks for particular kernel calls, but we also have regions. But in that case, the user has to explicitly annotate the code with these regions if they wanted to do something with that. Yes.
And Natalie had a question for the general audience saying, did anyone of you attending had an experience of actually motivating end users for energy efficiencies other than our panelists? You can basically, if you want to speak up on that, feel free. And then I actually, by the time somebody raises their hand or shares something, I would actually transition to the next session so that they have still enough time.
So if I may go, last week I was in an SPH conference, basically about particle-based methods for engineering and astrophysics, and I gave a similar talk that I gave today, and a little bit more detailed, of course. But everybody there were quite interested in thinking about energy efficiency. And one thing, so we also at the university have a, well, rather small cluster around like 160 nodes, I think. And we have been in collaboration with the admins of that cluster as well. So they had quite a lot of difficulties convincing people to increase the performance of their code or do their job allocations more strictly so that the job scheduler can work better, let alone energy efficiency aspects. But I only wanted to comment on Fumiyoshi's slides, saying this is one of the ways that maybe can include more people to think about how they can do these. Because every time I talk to a researcher running a simulation or something, everybody is interested in increasing their energy efficiency because of environmental concerns. But when it comes to some effort, not a lot of people want to put that effort. But one of the most important points that we are now discussing and seeing is that domain scientists are more interested in their jobs finishing whenever they submit it. For example, if they submit a one-day job, if that takes 20 hours or 22 hours, they don't care as long as it finishes. So that, I think, is a perspective that we are now seeing, at least, and can be useful for motivating users. And what I saw from Yoshi's slides is a great example of somehow motivating users to be more mindful about these. And I will share these also with the people we collaborate, and maybe we will also come up with a better motivation for the users, hopefully. Thanks.
Can I say a provocation?
Yes.
Why don't you just make people pay more for the time they spend on the cluster? This is a great motivation to optimize code, isn't it?
Yes. It's difficult to find the balance between fairness and charging more. So, but this is a good point. Yeah.
Yeah, again, it's a provocation, but of course, usually domain scientists are not expert software engineers, so code optimization is the least of their problems, but it's also maybe the first source of energy saving, because if you can just do less computation, everything is easier. But in research group, sometimes it's hard to find a proper software engineer because the budgets are spent on domain specialists. But if the cluster is so expensive that it's worth hiring a software engineer, maybe things could change.
Okay, thank you all very much for all these interesting perspectives and the short talks. If you ever see the speakers at one of the conference, engage with them. You now know their background and how to actually improve what we're all trying to achieve. So thank you very much. And with that, I'm going to wrap it up and hand it to the next session.
Okay, thanks, Matthias. That was great. So next session is a session on Green 500 measurements and methodology in general. Thomas Ilsche from TU Dresden will be driving this session. Focus will be on lessons learned and some of the ongoing challenges. And we are also eager to hear of some of the use cases and lessons learned from adopting such methodologies when monitoring an actual system. So Thomas himself is a research scientist at the Center for Information Services and HPC at TU Dresden. His research interests include energy measurement data processing infrastructures, and performance analysis and optimization for HPC systems. He received his doctorate in computer science from TU Dresden in 2020. And with that, over to you, Thomas.
Thank you, Sid. Let me just quickly share the screen. Okay, I hope you can see the presentation now and hear me all right. If not, write it in chat, I guess. So I am going to just give a quick overview of the Green 500 and its power measurement methodology, really just a top-down high-level view, and then we will jump to the detailed talk, and I will wrap it up at the end with some outlook on the changes that we are planning on the ideas we have for improvements in the future. So this is the current Green 500 list, and I borrowed the slide from Wu Feng from the BOF presentation at ISC just a couple of weeks ago. And this has actually been quite a disruptive Green 500. So as you probably know, the Green 500 is now part of the top 500, and it's the same data set, just a different ranking. Instead of ranking by the top performance, we rank by the performance per watt. And as opposed to the top 500 itself, which has been relatively stable in the past, the Green 500, this ISC has had a lot of changes. So all of these yellow systems in the top 10 of the Green 500 list are actually new submissions from this list. And they are also all the same architecture, which is the NVIDIA Grace Hopper systems. So this new architecture has been shown to be very energy efficient, with many submissions surpassing the previous top submissions. So even the top submission is now only ranked 4, and we have 3 new systems on the top spaces. And even we have additional new systems along the list. This is actually quite a rare event to have such a disruptive change. And so what is the point of the Green 500? What's the motivation? And I don't want to go back too far in the history of that, but similar to the top 500, we kind of have a friendly competition here between the vendors who can make the most energy efficient architecture, both in terms of the compute part, but also in terms of some of the surrounding infrastructure that's participating. And it's also a sort of a research data set in order to understand the trends in energy efficiency. So there will be lots of plots for, trying to predict the power consumption for future systems. And this was very important for the path to exascale, which we have now sort of reached with the systems right now, that we needed a certain level of energy efficiency, which I think was 50 gigaflops per watt. And now we have a lot of systems that can reach this. And so this puts us firmly in terms of energy efficiency in the exascale area. Now, how do we get these values? All right, we have here the ranking of the gigaflop per watt. If you see my mouse cursor, that's nice. Let's see. We have this ranking, and the question is, how do we get to this number? And it's a little bit more difficult to get to this number than to get to the top 500 number, which is also not easy. But the performance is just measured by the theoretical amount of flops you need, divided, and basically considering the time it takes to perform them. But here we need power. We need to measure the power consumption or the energy of the system that is under test here, that is running the benchmark. And to mandate that, to have some rules to make sure the measurements are useful and correct to some extent, we actually have the measurement methodology. So this is a PDF document, and it has some detail on it, but the most important thing, the central thing, is actually this table, which shows the requirements and the 3 different power levels that the power quality levels that are available to choose from. So it's not just one basic level, but it's actually distinguishes 3 different levels in terms of the quality of the measurement. And this is sort of a cheat in order to avoid the trade-off between having a low barrier of entry for the system. So we don't want to have an empty list, but also we want to allow systems to have a good power measurement and to, to go even beyond the basic requirements in terms of getting to these numbers. And so I actually have the bottom half of the requirements table here listed, and I will go briefly through that because the bottom half is a little bit more easier to explain. So in these three levels, one of the actually important distinguishing factors here is the machine fractions. So in the lower levels, level 1 and level 2, you only need to measure a certain subset of the system, and you can extrapolate from a subset to the full machine. This is important for systems where you have a large system, but you also have a instrumentation, a power measurement instrumentation that is not meant to monitor the full system, that is basically only a vehicle to make a submission. And for these kinds of systems, there is a compromise in level 1 and level 2 that allow you to, don't have to buy a power meter for all of your racks, but you can choose some of the racks to measure. And the thresholds, how much you have to measure is different for level 1 and 2. And level 3, you actually have to include all of the subsystems that are participating in the benchmark. So all of the compute racks and also some of the other stuff that's participating. When it comes to the subsystems, this means basically compute nodes versus interconnects. Most of the time, storage is not considered to be participating in the benchmark because it's a compute benchmark after all, and it can use local storage. So for all the levels, the compute nodes must be measured. But for level 1, and to some extent for level 2, you can estimate some of the participating subsystems like interconnect hardware that can be estimated from data sheets or similar things, or from measurements of a similar setup but outside of the system. This is again a compromise in order to allow more systems to make a level 1 submission. And we have the location of the measurement, which is actually the easiest possible for all of the levels, where you can just measure upstream of the power conversion. But for the lower levels, you are allowed to measure at closer to the consumers, with the power conversion just being a modeled component instead of measuring the power conversion. And finally, this is probably the most important aspect of the whole quality level, is the accuracy that's required, which is 5% for the level 1, 2% for level 2, and 1% for level 3. There's some certain references, for instance, for the spec power meters and ANSI standards that help you to understand the accuracy levels here. But this is really sorting out what kind of technology you can use for the measurements here. Then we can go to the top half of the quality levels, where we are concerned with the timing properties of the measurements. And this is a little bit of complicated setup here. I'll probably not go too much into detail, but basically with level 1 and 2, you're having 1 sample per second as a requirement, which is actually sometimes also challenging for level 1 submissions. And for level 3, you're required to have a continuously integrated energy measurement, and then you get the power consumption by dividing the energy over the time. And there are certain sampling requirements for the internal measurements for level 3. Then there are some reporting timing requirements, just how many data points you have to provide with the submission, which is part of the document. But to be honest, the submission process does not really take care of these aspects of the list. And so for instance, these different values, the data points, the 10 measurement that you are required to submit for level 2 and level 3 are not much used in the website, so they're not published. Okay, so this is the quality levels, and now for my last slide before I hand over the presentation. I just annotated the list that we saw initially with the quality levels because this might be interesting to see. We now have the top 3 systems here with level 1 quality and level 2 quality. Then the previous number 1 system that we had for a while was a system where we unfortunately do not even have a power quality specification. So it is just a number that has been submitted, but we do not actually know how. And this is you know, a point of discussion. What is a list where we have, you know, in the top 10 and even at the number 1 space a submission with no understanding of the accuracy of the numbers. And we have one system in the top 10, which is Frontier test system for Frontier, that has a level 3 submissions. But I've been told the system has actually now been integrated into Frontier, so it's no longer a separate system anymore. But this is actually quite representative. There's lots of level 1 submissions, some level 2 submissions, and very few level 3 submissions. And this is not surprising. But the nice thing is here, I can now hand over to Toshio Endo, who is a professor at the Advanced Computing Research Division at the Tokyo Institute of Technology. And he is also involved with the Global Scientific Information and Computing Center that hosts the Tsubame 4.0 system that has a submission in the most recent top 500 list, or green 500 list for that matter. And it is one of those level 3 submissions. So I'm looking forward very much to the presentation of how they have achieved a level 3 submissions, because this is actually very different for the different sites and different, you know, sub-communities. And so with no further ado, I would hand over to Toshio Endo. Thank you. I hope you can present if there's anything we need to do. Then maybe
yes.
Sid can help us out.
Okay, can I share my screen? Yeah.
I hope so. If not, I would assume Sid can help us, or
Oh, here.
Natalie.
I'm here.
Yeah. Toshio-san, do you see the share screen option at your end?
Where? Just a moment.
For me, it is a green arrow on the bottom of the screen.
Yes, we can see it now.
Thank you.
Is the screen okay? Okay.
Yes.
Sure. Okay. Hello. I'm Toshio Endo from Tokyo Institute of Technology, and let me report our Green 500 measurement using the Tsubame for supercomputers. This slide shows our supercomputer series named Tsubame, which has started in 2006. It was Tsubame 1 and Tsubame 3, and until this March, Tsubame 3, the previous system, had been working. On this April, the new system, Tsubame 4 has been installed and started, and integrator of Hewlett-Packard Enterprise. So this shows the system overview, and the computing nodes are 240 HP gray nodes, each of which are 2 CPUs and 4 H100 GPUs. The system's total computation speed is 66.8 petaflops in FP64, and in theory, this is our peak. Also, this slide shows range, and the system consists of 30 racks. Out of them, 23 are for computer nodes, and storage or management system uses 7 racks. This shows more detailed information of the systems. Each of 240 nodes has 2 AMD EPIC CPUs, 96 core CPUs, and node has 768 gigabyte nodes. Also, 4 H100 GPUs. Also, we are using customized variant of H100 with a bit larger device memory, but it is HBM2E, so slower than normal HBM3 SKUs. So basically, the system is cooled by a chiller, and power consumption is in theoretical value. It is 1.8 megawatts, but usually it is much smaller, and around 700 kilowatts in normal operation. The system is installed in our new data center. Actually, the building is very old, but it has been renovated for power, and now it is a new data center. Server room has the area of 200 square meters. So this slide shows one of computer nodes with 2 CPUs and 4 GPUs. Actually, the node-wise cooling is using hybrid method, that is, direct liquid cooling method is used for CPUs and GPUs, and also we are using air cooling for host memory or other parts. So anyway, we can see cooling water pipes here. And this shows rack level cooling and chillers. So computer nodes installed in a rack with a chilled door. Also, each rack has rack level CDU at the bottom of each rack. So DLC water is connected with rack CDU. Also, chilled door is using water from rack CDU. Also, there are heat exchangers, and there are chillers outside of the buildings. So anyway, all of all of the IT system depends on chillers. And let me explain the system's power supply and power meters. Basically, we are using 415 volt power supplies for computing rack and chillers and pumps and so on. Also, we are additionally using 200 V supply, but it is fairly small. So in Green 500 measurement, we are using power meters, and the system has 5 power meters, each of which is Schneider PM meters. Power meter 1, 2, 3 are for computing racks, and number 4 is for water cooling facility, such as chiller and pumps. Number 5 is for air cooling for the room, but actually room air conditioner uses very small fraction of powers. Anyway, PM 1, 2, 3 are used for Green 500 measurement. Here, let me mention that PM 1, 2, 3 includes all subsystems of computing racks, including computer nodes. That is natural, but it includes power for rack CDUs and chilled door of each rack. So here I have shown our power supply and meters. Using those meters, we have conducted Green 500 measurements, and we consider this measurement conforms level 3 regulation. So when we obtain average power, we use energy values accumulated by power meter 1 to 3, and we use a difference of an energy between 2 timings. One is the beginning of core phase of HPL, and the second is end of core phase. So average power is computed by difference of energy divided by core phase time. So the result average power for computing rack meter is 732 kilowatts, and this shows the fluctuation of power during HPL. So parameter 4 is measuring chiller and pumps, and whose average power was 89 kilowatts. This is excluded from calculation here. Parameter 5 is for room air conditioner, and it is negligible. So anyway, in this case, HPL speed of this measurement was 25.4 petaflops, and average power is 732 kilowatts. From two numbers, we get energy efficiency, which is 34.7 gigaflops per watt. So this number this system is ranked as number 31st in top 500 and number 25th in GRI 500. So actually, this number is not good as our previous expectation. Actually, we consider it is very bad. So let me explain this, our situation. At first, HPL speed is more slower than other systems. And in this submission, only 215 nodes out of 240 nodes. So we want to use more. Also, HPL efficiency, which is impact speed divided by peak speed, is only 42%, while other sites using H100 max 16% or so. So our system is through here. So we are expecting uneven performance of GPU during measurement, such as by unexpected clock throttling, but we need more investigation. So also there are issues related to conditions for power measurements. Basically, level 3 measurements tends to show was L1 or L2 because we have to measure more subsystems. In our calculation, we excluded chiller power, but we include power for rack CDUs, chilled doors. We think this is required in level 3 regulation, but we also include management nodes or shared storage, which is not used in HPL measurement. Also, there are unused nodes, around 10% nodes are not used, but they are, some of they are powered on. Anyway, our measurement suffered from lack of times for schedule restriction, and we had only a half day for measurements and optimization. That was unfortunate, and we want to have a chance to retry for this autumn, but this is under discussion. Okay, so thank you for listening. And let me make a short announcement that Tokyo Tech will be merged with another university for medical university, and the name will be changed to this Institute of Science Thinking. Thank you so much, and I'm not sure about my presentation length, and I'm sorry. Yes, and thank you so much.
Thank you, Toshio. I was hooked from the start, and this is a lot of useful information, I think. I think we have a few minutes time to have a discussion on this specific. Yes, you can leave this slide. This is the best slide on this specific presentation. So if there are some questions in chat, we can take them now. I don't need much time at the end. I would actually like about this slide to make a few remarks. First of all, I think it is great that you measure and present the chiller part and the room part here. this is very helpful for us to get an understanding of the domains and the scopes that are involved here, because one of the aspects that we want to revisit in the methodology is actually a better definition of the measurement scopes. Currently, it basically says you have to measure all the participating subsystems, and integrated components like integrated cooling has to be included. But then again, that's a bit vague. And maybe we would like to be a bit more precise. I think your interpretation right now that you have to include the cooled doors and the CDUs is in line with the definition for the level 3 submission. And also, yes, you don't need to add the chillers and the external pumps to the value. So I think you did everything right, but this is great data to have. One question though, I'm a little bit surprised by the variations that you see in the chart on the bottom left. I would have expected from such a coarse grain measurement to be a little bit more smooth here, especially since you measure once a second. Can you explain, do you have a understanding why the variations are so strong?
You mean this variation is larger from expectation or smaller from expectation?
So I was expecting more a straight line, and then the drop off, right? So this drop off at the end, the last 30% that we see the power decline due to balance issues. This is very common, but the ridges and the valleys and on the earlier time is a bit surprising to me.
Actually, I don't have a good answer. For example, since the execution of HPL is not optimized sufficiently, so there may be some phases for more computation and other phases for more interconnect communication. But anyway,
Okay.
we need more.
Yeah. So I've seen one run that had strong variations during the compute. This was on a CPU system in Dresden that had very regular patterns, actually very short intervals where the power changed drastically. But this was actually a symptom of a bad configuration. And when later on we improved the performance and the configuration, it went from very changing a lot to a smooth power consumption. So in a sense, maybe having these high variations is also for your system a symptom of that there is a bit more room for improvement in the configuration, as you hinted later. So maybe in your second try it will look a bit different.
Yeah, thank you so much.
Yeah. So there is a remark in the chat from Aditya. Just reinforcing that we should be clear what need to be included and what's not. Yeah. And Gert Wenberg has raised the hand. Please open the microphone and ask your question.
Oh, thanks. Might be a mistake, but I have a question regarding the accuracy of the power meters and the need of that. I said we make a contribution level 2 because we were a bit insecure about that. You look for sampling rate of 5K, and we have there multiple meters, PDU meters with 4K, and this is but we made measurements to control that with better and came to an accuracy of 0.5 to 1%. So I have the question: how strong are that requirements for a level 3 contribution?
So I have an opinion on that, but I have to say that I'm not necessarily the authoritative decision entity here. In my professional view, the sampling requirements are actually reverse. This is a bug in the methodology specification as this is currently published. This is in a sense, this is a known issue because it has 5 kilohertz for AC and 120 hertz for DC. And clearly 120 hertz is a sampling frequency that's very closely related to 60 hertz measurements, so 60 hertz power, AC power measurements. So that's my one issue I have is that. And the other issue is that I don't think all of the measurement devices that have a good accuracy specification actually are super transparent about their internal sampling rates. And I don't think we should require internal sampling rates. I think we should focus on good standards on accuracy classes instead of these sampling rates. So there is a good reason for requiring high sampling rates, but the reason is accuracy. And if we can make sure that accuracy is right, there's actually different ways to achieve the accuracy. So you can have, for instance, a proper band filter, low pass filter in before the measurement, and then the sampling rate has to be matching the filter and not just some arbitrary number that's in this document. So I would certainly not reject your submission on the grounds of the sampling rates. If your accuracy is well documented, that in my opinion overrides the sampling requirements. And to round this up, it is my personal point. One of my personal points in the updated document is to remove this sampling requirement because it is just confusing. So
okay, thank
the
you.
long answer, I think.
Okay.
But, you might have noticed that I have a personal relationship to this part.
No, I think most of us are not electricity engineers.
So
thank you.
So I think we need to wrap up soon. But there was a question specific for Tsubame 4 and Toshio. Maybe you can make a quick answer, then it would be we can fit it. Why did you procure a system with lower inlet water temperature and a chiller instead of continuing with free cooling?
I have written a simple answer to the chat. Actually, yes, we wanted to do warmer water for energy efficiency, but vendors, including HPE, told us that we want to use cooler water for cooling conditions should be relaxed for H100. So actually, when we are discussing node configuration, many of vendors cannot use actual H100 nodes. So yes, we wanted more optimized systems.
Okay, so I'm gonna need to wrap this up. So I'm gonna just show a final slide, basically. Hold on, and change the screen sharing. Thank you again for the presentation and the discussion, Toshio. That was I enjoyed it very much, and I think the discussion in the chat also speaks to that. So
thanks so much.
I just want to bring one of those pictures for the motivation here, why we're talking so much. This is the current share of systems in the top 500, and therefore the green 500. And there's a majority of systems over 60% where we actually don't have a power consumption. And then there's still 10, 11% where we have a...
Thomas, they're not sharing.
Oh, okay. I'm sorry.
I was seeing it.
Let me try again. Do you see it now?
Oh, I think Toshio has to stop sharing his screen.
That's funny. I'm seeing it.
We see it. Thanks.
Good now.
Better now.
Okay, good. So this is just the pie chart I was talking about. A lot of systems with no power and still systems with no power quality level. So we don't really know what the power is worth. But there are level 1, level 2, level 3 systems. And there's a trend here, which I'm going to skip now, actually, because we have used this time for the discussion. I want to briefly go into the methodology team and the update process that we are having. So this is just the contents to represent the document we are talking about here on the right. And what we did here is we surveyed some of the submitting sites, and we got a lot of great feedback. And we are keeping to reach out to sites that are submitting or that are not submitting power numbers to find out what can be improved in the document. And we appreciate every kind of feedback we get. And so it is a clear message that it needs to be easier to submit power information. So this goes from improving the text to simplifying levels to relaxing some of the requirements that are actually not met a lot in the practice. So most of the submissions of level 1 are really struggling with the 1 sample per second requirement. But at the same time, we want to retain a certain quality to make the data useful for the purposes that it's supposed to be useful. So this is sort of our agenda in the team, that the changes we want to make. So we have the text changes on the one hand, which are small changes, structure changes. Examples is an important part, to add more examples to give people some concrete ideas, and also to provide a motivation that's a bit better. We've talked about users and motivating users before. And then the other part is basically the requirement changes that affect the submission. And to improve those, we have the system boundary definitions that specify the domains that we have to measure. We want to be more clear there. We have some timing changes to simplify stuff, which includes actually also these sampling rates that we talked about, the accuracy requirements. And we like to make it less complex and try to simplify the changes, even though there are some discussions also going on with introducing a new level 0 to kind of get rid of those submissions where we don't know anything about the power values. And with that, I'm going to the final slide here. So if you want to be, you're more than welcome to join our discussion, a regular discussion on the power measurement methodology here. You can just send feedback to me or Natalie. So you have the email addresses here. We are also interested, especially from sites who did not manage to make a submission to the Green 500 because of some reasons. The only asterisk I have to say, if your reason is you didn't have the time, that's not necessarily helpful for us. It should be something that was an issue with the methodology document or the methodology itself. So yeah, here's the information to join us. We try to be very open in our update process, but we are very slow as well. I apologize for that. It is not the fastest ship in the ocean, but we hope that we are getting to some island with the next release anytime soon. So there's an internal review process. We have automated builds of the document. So we're trying to have a open and professional collaboration on this. And with that, I think I give back to Sid, right?
Thanks, Thomas. Okay, the last session Certainly not these very exciting. So this third session is on sustainability metrics for impact. Really, the focus is more on identifying different sustainability metrics across the entire system procurement session, right? Right from designing to procuring to having the system data center operational, a discussion on the different metrics that could be ideal. This is again a panel-driven session by Robert Bunger. I hope I'm pronouncing the last name right. Robert is a program director within the CTO office at Schneider Electric, currently working on the liquid cooling initiative and based in the United States. Since 21 years at Schneider Electric, Robert has held management positions in data center standards, customer service, technical sales, offer management, and business development. He has also lived and worked in Denmark and China, where he supported data center solutions, business growth in those regions. Prior to joining Schneider Electric, Robert was commissioned officer in the United States Navy and served 8 years in the submarine force. He holds a Bachelor of Science degree in Computer Science from US Naval Academy and an MS in Electrical Engineering from Rensselaer Polytechnic Institute. With that, over to you, Rob. Thanks for driving.
Thanks, thank you. Yeah, I didn't realize you'd be pulling up the old bio. Can you guys hear me? Okay.
Yes, we can.
Okay, great. Yeah, so if the panelists could, if you're able to, hopefully get your cameras on. What I'm excited to do is host a panel on metrics, and just so you know, so I do work within the CTO office at Schneider Electric and have been involved in some of the research and thought leadership we have done around, metrics around the facility aspect of data centers, of different sustainability aspects. And what we want to do here in this panel is focus on kind of two areas. First would be the design and procurement. What is the industry focusing on? What should we focus on? When you're designing your HPC as well as procuring it. And then the second is in operations, and obviously, you can, okay, still doing okay. So obviously, I think the industry's done well with regards to energy efficiency and made a lot of progress, but we do want to talk about everything. So if I could, I'd like to have our panelists introduce themselves. So let's start with Torsten. I guess, are you on? Can you hear me okay?
Yes, perfect. I can hear you, Rob.
All right, great.
Yeah, great to be on. So I'm Torsten Wild. I'm working for Hewlett Packard Enterprise, and I'm the lead architect for HPC system power and energy management for our Cray EX supercomputers and post-exascale. And I also have been working at the Leibniz Supercomputing Center in Munich, Germany, mainly focusing on energy efficiency and also how we can describe or assess the efficiency of direct liquid cooling. So we had the first direct liquid cooled supercomputer in the world at that point in time. And we made a claim that we saved X amounts of power and energy because of that, but there was no metric that we could actually use to show that. And so I was involved in some of the efforts trying to develop something that might be better suited than just PoE and the workload efficiency or performance.
Great, thank you. All right, Jason, I think you're on. Can you introduce yourself? Jason?
Jason, we can't hear you. Leave you're muted.
All right. Well, hopefully, Jason, you can hear. You're there. We'll switch over. Eric, I saw you're on. Can you introduce yourself?
All right. Can you hear me?
Yes.
Yep.
Okay. Yeah, my name is Eric. I work for Vantage Data Center, Principal Mechanical Engineer. Glad to be here. And also, I was involved TC 9.9. I'm currently program chair. What else? Yeah, passionate about energy efficiency. Glad to help.
Great, thank you. Okay. Back to Jason. See if you're still on. Are able to get on. Okay. Well, let's get started. So I have a set of questions, but we'll let the conversation go where it needs to. And so I guess first, so when you're thinking, and it's good. The intent here was also to have operators as well as vendors perspective on this. And so from a designing perspective, so as you're in first concepts of deploying a new HPC system, and I'd like to think about this both with regards to the systems right around the HPC and the systems and the facilities going into. Are there specific metrics that you're currently targeting during the design phase, like requirements you're putting on the designers as you're looking at the compute and the facilities? So I'll first start with that, and we'll go around it and see what's there at. So I'll start with Eric, actually, as get your perspective on that as a kind of an operator.
All right. Well, I'm on design side, but I'm familiar with operation.
Yeah.
So I think the question itself is a timely, but it's very complicated question. And as we are moving quickly on the liquid cooling deployment, it is really a Wild West field because in many places there's no such a great metrics for liquid cooling efficiency. People often use the total cost ownership, TCO, to compare. But in my opinion, there should be I would say another metrics indicate the total whole life carbon emission of the ownership. That will include the both embodied carbon emission and also the operational carbon emission. And this will provide us the baseline to think about the decarbonization efforts. And so as we all know that ASHRAE and other organization has been putting a lot of efforts in the decarb efforts. So for those who are aware, actually, there's MEP 2040 net zero goal or 2040 efforts. There are heavy focus on working on the EPD data, especially working on the whole life carbon emission for the large mechanical equipment, such as chillers and cooling towers. On the other hand, we just need a good set of EPD data for liquid cooling servers, right? We don't have those data available or easily available for us to use to compare life cycle comparisons. And so in my mind, I really think it's much needed data. And also, Vantage is the colo provider. So we are concerned often about the violation of the service level agreement, such as server temperature, and also we also look at the differential pressures across the TCS loop and also pump status, right? So all these are important to us, but not necessarily are really a KPI for the sustainability metrics. But on the liquid cooling vendor perspective, many are really, as mentioned before, many actually are looking at TCOs, and some are to look at the server densities. And also from the ITE equipment perspective, some are focused on the computational efficiency or server utilization rate. So again, there's a lot of talk on this topic, but I want to just bring out on the topic. I think PUE by itself is not a good metrics because it doesn't really include the server fan power. So in order to compare the air cooled versus liquid cooled, you really have to do adjustment on the server fan power to your air cooled servers in a way to really compare apple to apple. Back to Rob.
Yeah, thanks, Eric. You brought up a lot of good points, and I first want to say thanks. I think you're currently at ASHRAE right now.
Yes.
Yes, participating in this forum. So thanks for taking the time. So yeah, liquid cooling, and you know, I think as we get into operations, I do want to touch on some of those metrics, because I think it was this group here in LBNL that pioneered the TUE metric, which was sort of a bit of an answer to the problems that we see with liquid cooling and PUE. But getting back to in the design phase, you mentioned the carbon life cycle, and I know as a vendor, we're getting you know, lots of pressure from our customers on being able to provide that EPT data, and so we're working hard to ensure that that is available for all our products. And you know, so I do want to ask Torsten, how is, you know, on the compute side is much more complicated. So there's obviously energy use, but then there's the embodied carbon aspect of it. How is that going on your end?
Yeah, maybe let me split it into two things. One, the embedded carbon, and one just how we try to improve efficiency. So I think it's like with everybody in the industry, like you said, carbon accounting is becoming more and more important to our customers. And like you said, the challenge is that we don't have good, currently at least, the models we are using are really based on estimation or kind of averaging across specific industries. Yeah, to kind of come up with at least somewhat usable estimation of embedded carbon. What we are currently working on is really with our suppliers to have them be able to actually provide the data we need to us. Yeah, when you think about millions of components on a motherboard, then yeah, you need all that information from somewhere. And so hopefully we have, no, not hopefully. So we do have some first results where we look more closely into very more component-specific carbon estimations. And that looks already a lot better or more real, I would say. So that's my personal opinion there, than the estimations, yeah, that we had to begin with. But I mean, I think the industry is struggling with that overall. And I think we are moving in the right direction in that regard. Then the other side is when we think about carbon reduction. I mean, our company produces servers that other people run. And so part of our own carbon footprint is actually scope 1 emissions that are the emissions caused by our customers by using our products. And so one way that we try to address that or reduce that is actually we do look into ITUE, which is part of the TUE metric, yeah, that you mentioned, which is really the power going into our servers and the power then used by the compute components. Yeah, mainly CPU, GPU, memory. And we actually tracked that back. So I have some data for you here just for fun. So the earliest data that we have is from 2007, and that was an air-cooled supercomputer where we had ITUE from 1.75. Yeah, so that was really an air-cooled system at that point in time. And I think what we should not forget is that usually air-cooled data centers are less efficient than liquid-cooled data centers. Yeah, so the 1.75, when I tell you the later on, might not sound too bad, but then you have to add like the PUE of that data center to the overall, and then it's actually quite bad. So we improved that with hybrid cooling. Yeah, so where we have a mix of liquid and air cooling still in 2012. And so there we had an ITUE of 1.47. Yeah, so which is like a 30% reduction roughly of overhead that was caused by mainly fan power and other things in the system, yeah, that we air cooled. And by moving to direct liquid cooling, so like the CREX platform in 2019-20, we have roughly an ITUE of 1.3. Yeah, and in my mind, that's really a good metrics to track. But we are also seeing, in our case, that we are getting closer to, I wouldn't say an optimal, but a point where kind of the improvement is slowing down. Yeah, so we can see that. And I think the biggest part that's still left is really the power delivery. Yeah, so that still kind of accounts for 20% of the overhead, in our case at least. So yeah, I think when really looking at efficiency or sustainability, we need to look at everything combined. Yeah, the data center by its, yeah, how the data center operates. I think also what temperatures are more efficient for specific data centers, and then be able to use that temperature range in our system so that actually we can avoid chiller use, like what we saw at Toshio, that he said, like the chiller actually added some of the overhead. And so I think moving to chillerless, what they had before, is what we want to do. But of course, the components are kind of working against us currently, at least because they are pushing us to requiring lower cooling temperatures because their T-case requirements are lower than what they were in the past. And so I think there's an interesting contention, I think, moving forward to get back to higher cooling temperature ranges where we can use absolutely 100% free cooling in most of the places on Earth, which will definitely help us. And maybe the last piece that I want to say is also, I mean, so still that does not really allow us to push our customers to reduce their carbon footprint, to help us reduce our carbon footprint. Yeah. So the other approach that we are also having is trying to develop features that would allow us to use our systems better or more efficient in their environments. Like, for example, having supporting higher inlet temperatures, maybe reducing performance during times where that higher inlet temperature gets too high because of outside conditions. So rather than requiring chiller, we just reduce the performance for that short period of time. And we are also looking actively in how can we enable customers to use or to have heat reuse scenarios where the heat quality that we could produce is higher quality than what traditionally we can do. To all feed back again into data center efficiency and heat reuse and supporting the overall carbon reduction.
Yeah, and a point I want to highlight that you said is, so you and I as vendors, right? Part of our carbon reporting is downstream use of our products,
exactly.
right?
Yep.
So we do care because unless we're able to reduce the impact of our product use, we won't be able to meet our sustainability goals. So that's great to hear, to put in those options to allow the users to optimize the operations of it. So I think Jason is online. Are you there?
Yes, can you hear me?
Yeah. All right. Oh, you sound great. So go ahead and introduce yourself, please.
Sure. So I'm Jason Hick. I work at Los Alamos National Lab. I focus on program direction for HPC facilities, operations, and user support. I'm a sponsor of environmental sustainability at the site, focused on high performance computing. So that means that I encourage, shape, fund efforts, really new efforts in energy efficiency, water conservation, HPC metrics, things like that. I also co-lead the procurement team with Gert Svensson within this working group, and we work on providing useful information for all of us, really sites, to establish energy efficiency goals during their, or within HPC procurements.
Great, thanks. So I'll kind of put the question back on you with regards to as you're in the specification design phase of a system. Yeah, what are the things that you look at? What do you think the things you should look at with regards to sustainability? Is it more than energy efficiency? You mentioned water. What else is there?
Yeah, I would say, our site focuses, one of the challenges our site, and I think a lot of the customer sites face, not just us, is, a mission-focused, need when we buy a system. So in other words, there's a particular reason we're buying the system. We have to achieve or make use of that system in that way. Often those are seen as in opposition or in like a controversial play with sustainability goals. And I think the challenge I've had and many of us have is in not taking an all or nothing approach in either sustainability or in mission need, if that was a spectrum, one at each end, but taking a middle of the road. And I often find defining, requirements in capabilities is the most helpful in achieving that togetherness in how we procure our systems. So in other words, procuring things with a sustainable mindset, if you will, but yet still allowing us to achieve a mission. I think what you've already mentioned, getting more specific, we focus a lot on energy efficiency, and a lot of it is what we've achieved as a group here or a working group together over the years. So we look at things like the particular CPUs selected, what their computational capability is. We look at software that's provided and workflows. We look at application performance on the system. And so we track, and I think most of us do this, but it's very helpful to not just look at it as a, kind of like a top speed of a car, what's the flops on the system, but rather, when provided as a complete system here, what will this be, enable our applications to achieve? We do focus a lot on power quality. That hasn't come up yet, I think, in the discussion. I was looking over our recent procurement documents, and there's at least 2 or 3 requirements that are focused around power quality to make sure we keep our power factor up and are a good, if you will, citizen of the power, the local power grid. We do, it's a little heavy-handed to say we power cap because we don't, but we do list requirements for what the peak power of the machine can be at our site, what our facility can support. And we do look at water, quite a number of water requirements to achieve. And, what we have through the years succeeded in moving from a supply stream, potable water and highly treated potable water to into the waste stream. So we use almost exclusively, we use non-potable water to cool, direct liquid cool our systems. And that's been very successful for us in a number of areas. It's helped us maintain our equipment better because once you commit to treating the, if you will, the wastewater, they don't like us using that term, but the waste stream water and producing really clean, non-potable though water, we're able to, it doesn't foul up the equipment as often, which means you don't have to use those really harsh chemicals to clean your equipment. So let me turn it back over to you, Rob.
Oh, that's interesting. I didn't think about the water quality and the chemical aspect of sustainability, but that's good. And one more follow-up question for you, Jason. Does you have internal customers, right, that have their mission requirements. Can you get a sense on, is sustainability on their mind at all? Has it changed over the last 5 years? What are your thoughts?
I think that's a great question. I think, let me start where I was going to finish with that thought, which is, it is on their